All right, let us take a look here at our bell work. So we are given the following situation. We're looking at, in this case, some kind of angle theta here. And that theta tracing out, in this case, an arc that has a measure of 13 pi over 5. I'd say the biggest thing that I think threw a lot of people off, we see that 13 pi over 5. Man, that looks a whole lot like an angle, because it does. It looks a lot like a radian measure, but it is in fact not. It is in fact the arc length, and we don't know what theta is. And so this is 5. This is 5. Now, what pretty much everyone did, which is fair, this is an absolutely valid approach, is they said, well, I know that the arc length, or not arc length, but the area that I'm looking for, because ultimately that is what we're looking for, is what is this area right here. I know that that is going to be equal to whatever fraction I can compose. So either like theta over 360 or my theta in terms of radians over 2 pi times pi r squared. And we're looking at some fraction of my circle here times my area to get a fraction of the area. And either way is fine. And so the only thing that I'm really missing here is my value of theta. All we really need to do to solve this is to identify what is theta. So that's totally fair. And the piece of information that we can use to do that is, well, we know that the arc length is equal to 13 pi over 5. And similar to the area of the sector, the arc length is also going to be whatever this fraction is, either theta degrees over 360 or theta radians over 2 pi times my circumference. And so I have an equation, looks like two variables. I know what the radius is though. I have an equation that I can solve for theta. Now in this case, it doesn't matter whether you want to solve for radians or degrees. Just make sure that you're keeping your answers very precise, not rounding one way or the other. I would choose to do this in radians probably, mostly because if I get to make that choice and I choose radians, then my formula actually simplifies very nicely and the 2 pi's that I have here cancel. And so we end up that this should just be equal to theta in radians times our radius of 5. And so my theta in radians should just be equal to, dividing by 5 on both sides, I get 13 pi over 25 radians, which is a little bit more than pi over 2. A little bit more than 90 degrees. If you had done this for solving for degrees, you should have gotten that theta was equal to 93.6 degrees. Those two are equivalent there. And either one is totally fine. Regardless of which one you got, you would take it, you'd plug it in. We would say, okay, so that means that the arc length, or not the arc length, sorry, the area of the sector equal to, since I found radians, let's do my 13 pi over 25, all divided by 2 pi, times my area here, which is pi times 5 squared. 13 pi over 25, all divided by 2 pi. That 2 pi is going to multiply into the denominator. This should become 13/50ths, which means, again, that we've gone a little bit more than a fourth of the way around our circle. And this is just 25 pi. (13/50) times 25 pi. You could do 13 times 25, but why do that when we can cancel 25 divided by 50 is just 1/2. So a 2 will be left in the denominator. The 25 will fully cancel from our numerator. This should be equal to 13 pi over 2, and then our units are in meters, and we found an area, so it's meters squared. Yeah, it should be the exact same, because the degrees and radians are both referring to the same angle. It is the angle that is a little bit more than a fourth of the way around the circle.
You got 13 pi over 25 because it's negative r times 5.
So theta in radians times 5 is the arc length. So when you have your radian theta multiplied by the radius, that was like our shorthand formula for arc length. And so dividing both sides by 5, setting it equal to the arc length, dividing both sides by 5, and so this is the 13 pi over 5. Dividing both sides by 5 is the same as multiplying 5 into the denominator on my left-hand side, and so I get 13 pi over 25. But certainly we also could have divided by 2 pi on both sides and then multiplied by 360 on both sides, and that would also work. That would give you the theta in terms of degrees, which 93.6. Okay, that is a perfectly fine way to do it. That's totally fine. That works. Finding theta, that's great. But actually, we can come to the fact that we have a slightly more than a quarter rotation a lot faster. We can get to this 13/50 number a lot faster than finding theta, creating the fraction with our degrees and all that, in a very similar way to what we looked at with the sector area. Now, if I am looking at the arc length of a wedge, arc length of a circle, what is the arc length? What is it a piece of? It's a piece of the circle, but what feature of the circle? Arc length is a piece of the circumference. So it's like a one snippet of a much larger circumference. And go figure, if we had an arc length that represented, say, half of the circumference, how much area would we expect to correspond to that? Presumably, if we're accounting for half of the circumference, we would expect to account for half of the area. If we have a wedge that accounts for a fourth of our circle, then we would expect this measure here to be a fourth of the arc length, and we would expect this measure here to be a fourth of the area, and we would expect the angle to be a fourth of a full circle. It's all the same. It's all thinking about what piece of the circle do we have? What fraction of a full circle? How could I figure that out with my arc length? Well, do I know what a full circle would be in terms of arc length from the information provided? full circle of arc length is just the circumference. What's the circumference of the circle? 10, not just 10, 10 pi, 10 pi meters. All right. Our circumference here should be 2 pi r. R is 5. So this should just be 10 pi. And so what fraction of a circle does my arc length represent? Well, it should represent 13 pi over 5 out of a possible 10 pi. This is my fraction. Now from there, could we use that to figure out theta? Absolutely, we could use that to figure out theta. Multiply that by 360, multiply that by 2 pi. That'll give you your theta in degrees. It'll give you your theta in radians. That's perfectly fine, but that's overkill. We actually don't need theta because we're looking for the area. We're looking for what area does this correspond to? Well, if this is my fraction, which go figure, you do the simplification, you can confirm this for yourself. This is that 13 over 50. Well, we have 13/50ths of a circle, which means I should have 13/50ths of the area of a circle, which means I just take this 1350, multiply it by my pi r squared, and get the exact same thing that I got before, 13 pi over 2 meters squared. There's nothing wrong with finding theta using the formulas, all of that. That's totally fine. And again, if you want to learn all the formulas and all that, that's perfectly fine. It's a completely valid way to do it. But what I'm really trying to emphasize here is that this idea of thinking about how much of a circle we have, what fraction of a full rotation are we looking at, is one that's very nice and easy to use, to the point where it doesn't matter the initial condition. I could give you any kind of amount of information. I could tell you the sector area. I could tell you the arc length. I could tell you the theta in radians. I could tell you the theta in degrees. And it really should just be a two-step process to figure out any of the other missing pieces of information. Finding the missing fraction. What fraction of a circle does the given piece of information represent? And then from there, converting it into my new whole by multiplying by 360 to get degrees, multiplying by 2 pi in order to get radians, multiplying by pi r squared in order to get the piece of the area, in order to get sector, multiplying by the circumference in order to get arc length. Is that a, yeah, don't.
Why would you like this to I go to the numerator? 25 opposed to
The pi, you mean here?
No. What? Like the
25, so they both go to the numerator. It's just the 25 cancels with a 25 in the denominator. Yeah. All right, good question. Other questions here with our Bellick? All right, today, what we are going to do to kind of extend some of these ideas that we have been working with, largely still going to be the same. Two main differences, quote unquote, that we are going to address. First of all, up until this point, we've really mostly been talking about fractional rotations of our circle. If I rotate by a third of my circle, or if I'm rotating a 2/3 of the way around my circle, whatever it is, we're looking at less than one full rotation for the most part, or we looked a tiny bit with example 1 and 2 at a couple of instances where we were looking at more than one kind of full rotation. But ultimately, this fraction that we have been referring to has been a piece of our full circle. What we're going to be looking at today is a bunch of rotations. So maybe rather than looking at what's going on when we rotate halfway around our circle, we're going to rotate 60 times around our circle, but the logic is still going to be the same. If I rotate 60 times around my circle and I want to find the amount of degrees that I pass through, same idea as if I rotated halfway around my circle. You just take what it means to rotate once, multiply it by however many times you're actually rotating. The other thing that's going to be not super relevant, but we will see it kind of come up, it doesn't change too much about what we're doing, is we're going to be looking at speeds. We're going to be looking at this in the context of speed. Go figure, we have a wheel that's rotating. It makes sense to talk about speed, which gives us a time frame that we're going to be looking at. Really, these problems have been very static. Imagine this cheese wedge that just exists in the universe and isn't actually rotating, and we're kind of forcing it to rotate in our minds. But now there will actually be rotation. It will be occurring within a certain time frame. Picture, if you would, a scenario in which we have some kind of like track, and we'll assume that there's like friction on the track, and we have a wheel that's on top that's rolling down the track, and because of that friction is rotating down the track, is literally rolling, not just like sliding like a puck on ice. If we imagine that we are rolling down the track, then by the time that we have reached one full rotation, we'll say that maybe we start like here, we rotate, and by the time we're here, we have gotten back to that start. We have rotated fully one time. So one full rotation. In terms of our wheel, my question for you all is, how far would we have to have traveled in order to go from start to back where we are again? In order for us to fully rotate, what is this horizontal or this diagonal distance, whatever the case may be? How far would we have to move in this kind of linear way in order for us to fully rotate? It's going to be the equivalent of the circumference. So this distance that we see here, think of this as like the circumference of our wheel. See? Just like fully laid flat, this is 2 pi r, or the circumference. So imagine taking like a marker around this wheel and you're kind of using it like a stamp, and by the time you've fully rotated once, you'll have to have traveled the distance of the circumference. You have to travel the distance that is all the way around a particular wheel in order to find what we're going to call the linear speed or the linear velocity. Okay, so 2 new terms that we're going to talk about here. The first is linear speed. Linear speed denoted inappropriately with a v. Often when we use v in these kinds of contexts, we're referring to the velocity. There is something fundamentally different about speed and velocity. Does anyone know the difference between something's velocity and something's speed? Any physics aficionados? So the only difference, and this will be good for just math in general, but also if you ever take a physics class, the only difference between speed and velocity, they are functionally the same. They're very, very, very similar. And we're going to basically be using them interchangeably here, at least for now. Only difference, velocity can be negative, speed can be positive. So velocity cares about the direction that you are traveling. For instance, it is not the same to travel 10 miles an hour this way and 10 miles an hour that way. Those are fundamentally different, whereas the speed just says, well, you're traveling 10 miles an hour, you're traveling 10 miles an hour. That's all we really care about. Right. We'll see when we look at vectors, the actual definition of velocity mattering a lot, that direction being very, very important to us. But for our purposes, speed and velocity are going to be the same. We're going to just be assuming that we are traveling in whatever the positive direction is, and it'll work the exact same for us. Now, we said that that action of moving forward is like traveling along our circumference. If we are traveling around either a piece of our circumference or our circumference multiple times, what measure are we actually looking at? That we just discussed kind of before in the bell. So it's the circumference, which is related to what measure that we've recently been talking about? Length, which is arc length. Yeah. So this is like arc length over some amount of time. Which, just to remind ourselves, this is like that fraction. Times 2 pi r over some amount of time. How much of our circle are we rotating around? Times the circumference, times 2 pi r. Now, I said at the start to kind of preface this fraction up until now has been, we rotate a little bit more than a fourth around the circle. We rotate a third of the way around the circle, so on. Now, though, we're going to be rotating a whole lot of times around our circle. That's okay. We're still going to use this idea of like how much of our circle have we rotated around. It's just now going to be a number that's larger than 1. That's totally fine. Think of this fraction as referring to the number of rotations. Before it was like how much of a rotation, and now since we're doing more than one rotation, it's just going to be more than one. All right. Very, very similar to our linear speed is going to be our angular speed. Linear speed is how far we're traveling forward. Angular speed is going to be, imagine we have like a counter that's counting the amount of angle that we pass through as we rotate. In a single full rotation, how much angle would we pass through? 360 degrees or 2 pi radians? So either way is totally fine. So we could think about angular speed. This is like the angle per time, which is the same as, we're going to again say our fraction here, times this either 360 if we wanted degrees, but really for this, we're going to be looking at radians pretty much exclusively. And in fact, we're going to be phasing out degrees as we go. Radians are really what we're going to care about. But times 2 pi, or you could do times 360, and that would give you the angular velocity in radians as well, or in degrees as well, which is fine. No, we're pretty much going to default to assuming that it's radians. But you could accomplish the in degrees if you multiply it by 360 instead, which hopefully does not come as a surprise. Okay, so really the exact same thing that we just looked at. That's like how we converted to radians down here. This is like how we converted to arc length up here. And now it's just we're looking at radians over some amount of time and arc length over some amount of time. All right, so let's take a look at example 4A here. In this case, we have a bicycle tire with a radius of 14 inches rotating at 125 revolutions per minute. Revolutions per minute, that's just the same as rotations per minute. And we want to find both the angular speed in terms of radians per minute and the linear speed in terms of inches per minute. All right. So let's set this up here. What is our quote unquote fraction in this case? Yeah, it's the 120, it's the number of rotations in this case. So our 125 rotations. And then we're also going to have our unit time, which in this case is in minutes, rotations per minute. Now, something that we have kind of glossed over up until this point, we haven't really needed it, is unit math. We haven't done much with like fixing correct units, doing unit conversions, all that fun stuff. There is going to be a bit of that here. If you recall back to chemistry with like the picket fence method of like canceling units. The good news for us is that units cancel very similarly to numbers. So if you see a unit in the numerator and a unit in the denominator, they cancel each other out. If I want to cancel rotations in the numerator, where am I going to need rotations? I need them in the denominator as well. In fact, it'll be easiest if we just think about this as what's going on per a single rotation. And then what am I looking for my angular speed? What am I looking for in my numerator here? What units do I want? Radians. How many radians do I have per one rotation? Every time I rotate, I increase by 2 pi radians. That's just going to be a static number, always going to be 2 pi. Rotations cancels with rotations. Multiply everything through, and you end up with 250 pi radians per minute. We're getting there. We'll get there in a second. Yeah. So this is just for thinking about like the angle that we pass through. It doesn't matter how big our wheel is. If we spin around the wheel, then we're going to pass through the same amount of angle. What the size of the wheel will affect, though, is how far that wheel would travel as we spin. So that's the linear speed, which we'll do here in a second. Okay. Notice that this is essentially, we didn't use our formula really, but it was basically using our formula, right? We took the number of rotations, we multiplied it by 2 pi. That gives us the amount of angle that we pass through per minute. And I'm just showing you this unit canceling thing because we're going to have to do it for something like C, where it's a little bit difficult. So it's slight overkill now, but I'm trying to, jog the memory of those old chemistry days of when we were doing this. All right. For our linear speed, has our fraction changed? No. Still looking at 125 rotations as our quote unquote fraction. Still per minute. Still want to cancel this with a rotation on bottom. And per rotation, in this case, we're trying to figure out inches, the number of inches that we travel. That traveling distance is going to correspond to what feature of our bicycle tire? The circumference of our bicycle tire, which is going to be what? 2 pi times 14. A bit messy there. Pi times 14, which is our circumference. And this is in inches. And so what do we end up with? Well, plug into your calculator, I'd probably say, and this is going to be 3,500 pi inches per. All right, questions with what we see here? Hopefully very, very similar to what we were doing on Monday. It's just, again, now we've got that per some time unit. And in addition, we have this extra confoundingness of I'm not traveling halfway around my circle. I'm traveling, what, 125 times around my circle? But the logic is still the same. We take that fraction, which in this case is not really a fraction, it's just a full number, and multiply it by whatever unit that we are converting to, which in this case is either going to be an arc length measure, circumference, or an angle measure, which will be generally a radians, so times 2 pi. All right, let's take a moment. If we don't have any questions, take a stab at 4B. We're going to do 4C together, but let's take a stab at 4B. Now, for 4B, read very carefully what information I am giving you, just to be clear, because I don't want us to get confounded by any trickiness in that kind of information. So we'll take 5-10 minutes, take a stab. 4. Missing 0. Otherwise looks good. Perfect. Perfect. That's it. Now is 120 the radius? Doesn't have being intentionally obfuscating and tricky and obnoxious like that. Setup looks good for Omega. Is this the radius that we're getting? Just cut it out. That looks great. Super good. Perfect. So the diameter is 120, radius is half of that. Yeah. This is perfect. And then for this one, I gave you the diameter rather than the radius, so we just cut this in half. So 2 times 5 is 60 rather than. Well, that looks. You certainly could. You certainly could. That would give you inches per hour, right? And so then you need to figure out how can I convert the number of inches into number of hours. And there is a conversion factor. I think it's like 63,360 or something like that, inches in a mile. But I would do inches to feet and feet to miles. That's perfect. All right, very nice, very, very nice. Breezing through it. Fantastic, so for 4B, I'm gonna start similarly with how I did before. Start with the angular speed and then find the linear. For my angular, for both really, what is the quote unquote fraction that I am working with? So this is 45, not minutes per revolution, revolutions per minute. All right. And then just always with our angular speed, what do I do to this in order to convert it into my actual speed that I care about? To cancel revolutions on top, I need rotations or revolutions in the denominator. Either way is fine. You can use either word if you want to just translate it to rotations. That's fine. Even if you mix and match, that's fine as long as it's not confusing you that those are the same thing. Revolutions, rotations being the exact same. And then per one revolution, how much angle do I get in terms of radians? 2 pi radians, and then we'll do 2 pi r for the linear. And this would give me that I am increasing by 90 pi radians per minute. All right. For my linear speed, exact same fraction here of 45 revolutions or rotations, again, either way, is totally fine per minute. And in this case, I am taking my 1 rotation, and every rotation is going to move me forward by how much? Not just 60, but 2 pi times 60, whatever that circumference is. So 2 pi times that value of 60, which should give us 5,400 pi. In this case, no, not inches though. This is millimeters per minute. How could we have gone from omega to V in kind of one fell swoop? Because we kind of did something here that was a little bit redundant, actually. I think omega is like our theta, in this case in terms of radians, and V is like our arc length. So how do we normally convert our theta in radians to an arc length? What's that super simplified down formula that we have for taking theta in terms of radians and getting an arc length? Yeah, just multiply by the radius. So this here was just like times 60. And to go from, go figure, 250 to 3,500, that's just times 14. And so we could absolutely say that V is equal to omega in terms of radians times R. But that's just the same thing as saying that my arc length is equal to theta in terms of radians times R. These are just over some kind of time frame. So this is saying, hey, when I have, like, when this is per minute, it still works. But it does, in fact, still hold this idea. So I could have just multiplied by R to go from one to the next. And that absolutely would work. But then also kind of moves this more in the direction of memorizing a whole bunch of different formulas, which is what I was trying to stay away from with this. And so just maintaining that idea of taking like the fraction that we're working with. In this case, it's a full number of rotations, multiplying it by that conversion factor to get what we need. Nothing wrong with that. All right. Now C is going to be pretty much the exact same problem. There's only one thing that we're really going to run into as an issue, but we can certainly start this problem the exact same way that we started before. In this case, we are looking for the linear speed. So that's our V. What is our fraction that we are given? 500 revolutions, or if you want to write this as rotations, again, same thing. Either way is totally fine. I'm trying to be somewhat consistent. This is per minute. Very good. And then if I'm trying to convert to linear, well, I know I need to cancel number of rotations in my denominator. And then for linear speed, what should be in my numerator? 2 pi times the radius. So that's going to be 2 pi times 8 inches. And plug it into your calculator. I get that this is 8,000 pi inches per minute. All right. Is that my linear speed? Yeah, absolutely. This is a linear speed. Is it the linear speed that I have been asked to find? No. What have I been asked to find? Miles per hour, not inches per minute. Okay, so here's where all that chemistry work of setting up the picket fence and doing unit conversion, and keeping track of all that can come into play. Alternatively, what you could have also done is right off the bat converted the minutes into hours. So for instance, if I'm going to rotate 500 times per minute, how many times am I going to rotate per hour? Well, it should just be 60 times that. That would certainly work, but I think it's a little bit easier to just find that linear speed and then just adjust the units at the tail end. But whatever you prefer. Could have also converted 16 pi inch diameter into a number of miles, but that gets to be very, very small and again, kind of annoying. So I think this is nice because we have a nice workable number. So we have 8,000 pi inches per minute. Let's start with inches. I have inches in my numerator. I'm trying to cancel them, which means I need what? Inches in my denominator. Okay, that's not too bad. Does anyone know off the top of their head the conversion factor for inches into miles, number of inches in a mile? Yes, that is ultimately what we are going to do, which was converting first into feet and then feet into miles, which is exactly what we're going to do. So we'll use feet as kind of like an intermediary way to deal with this. We don't ultimately want feet, but we know that there are 12 inches in a foot. Now I need to cancel the number of feet, and I know that there are 5,280 feet in 1 mile. This is definitely information that you could expect me to like give you on like a quiz or a test or something. Like, well, yes, I think a lot of people do know that I don't expect you to have these. I'm not quizzing you on whether you have all these conversions locked into your memory, right? So certainly this would be reasonable for what I could give you. All right. So inches cancel with inches, feet cancel with feet. I end up with miles in my numerator, which is great. That's exactly what I was looking for. So now I am in terms of miles per minute. Still not quite what I wanted. Minute is in my denominator. So in order to cancel it, I need minutes in numerator. So we're going to multiply by minutes in the numerator. Ultimately, we want hours, and we can jump straight to hours without too much difficulty. All right. And in particular, after 1 hour passes, I have 60 minutes. And this is just multiplication. 8,000 pi times 1 times 1 times 60, 1 times 12 times 5,280 times 1 in my denominator. Plug it into your calculator, see what you get. If you plug it in without pi and then just tack on pi at the end because you like precision like me, then you get something that looks similar to 7.57 repeating pi miles per hour, which is great. If you love precision, that's fantastic. But miles per hour, we're not really going to be talking about 7.6 pi miles per hour. This is also, I believe, 23.9 miles per hour, although double check me on that.
How'd you get 23?
It's 7.57 pi. And so taking those and multiplying them together, you get 23.9. Pi is like 3.14, a little bit more than 7 times a little bit more than 3, you get a little bit more than 21. But either way is fine. I would be happy to accept either answer in this case for sure. All right. Other questions here? Hopefully, again, very, very similar to what we did on Monday with the whole like fraction and finding the radians and finding the arc length and all that. Now, slightly more, I'd say, cranked up just in terms of the unit conversions that we might now have to do, but hopefully not too much of not too horrible of a step up from what we were doing on Monday. Yeah.
Whenever you multiply the 45 rotations and 2 pi times 60, you get like a
Hmm.
completely different number. If you use pi, is that because, and at the end it's 5,400 like pi?
Yeah, so 50.
Pi like X sometimes?
So pi is just it's a constant. It's just like 3, it's a little more than 3.14, blah, 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 blah. And so I leave pi there just so that it's like as precise as possible because I'm never going to be able to write a decimal that perfectly represents that number. And so the most precise answer that I can give without any rounding is 5400 pi. If you plug it into your calculator, that whole thing into your calculator, you'll get like 20,000 something probably. And that's also fine, but that is a rounded version, which again is okay, but I'm trying to be as stringent as possible with what I have. The way that we can do it with our calculator without incorporating the pi is if you multiply everything that isn't pi together and then just stick a pi on it at the end. That's great. That'll get you there. Yeah, that's what I've been doing. So I do like 45 times 2 times 6, which is 5400, and then I put a pi at the end. And that's how I got the 7.57 as well. I did 8,000 times 60 divided by 12 times 5280, and that gives me the 7.57, and then I just stick a pi at the end. Good question. Other questions? All right. We've got a little over 20 minutes left. Tomorrow, unit circle quiz. You know exactly what it's going to look like. I'm going to hand you a blank unit circle. I'm going to say, fill out quadrant, one of the 3 quadrants that isn't quadrant 1, because I'm not that nice. And I'm going to give you probably about 3 minutes to knock that out. Quadrantal to quadrantal, so within the full like right angle bit, but I'll remind you of all that tomorrow. So unit circle game would be a good use of time during this point. That'd be fine. 4142 classwork also currently posted to Pearson. For extra credit, first 14, 1 through 14, so basically like the first half by tomorrow. And I think that's all I got. So I'd say one of those 2 things, similar to yesterday, one of those 2 things to work on. Of course, if you have questions as you work, please feel free to ask. I'd be more than happy to help. If you have questions that you'd like to go over on the board, so on and so forth, more than happy to help. So on. Yeah, you have the classwork in Pearson.